Tirupati is the only town in India.
Excuse me, sir. Sorry to disturb.
Yes.
Sir, now YouTube also live.
Oh, very good. Okay.
Shall I start recording, sir?
Yeah, you can start after maybe another 5 minutes, I think, because we want to start the program at 12.
Okay, sir.
We have another 10 minutes, so you can start the recording in another 5 or 6 minutes.
Okay, sir. Thank you.
So we are just chatting in the meantime.
Okay, thank you, sir.
Yeah, thank you. So you probably know about the Indian Institute of Technology. It's a number of institutions, sister institutions. We started out as 5 or 6, almost 60 years ago. And then about 20 years ago, we added some more. And then after another 6, 7 years, we added some more. So right now, we have the third generation IITs, as they are called, the 3G. Right. And we have one at this town, Tirupati, which is in the state of Andhra Pradesh. And there is a similar system of institutions which is dedicated to science rather than engineering. The IITs are dedicated to engineering. Right. And those which are dedicated to science are called as the Indian Institute for Science Education and Research, IISER. Okay. And Tirupati is the only institute which has an IIT and also an ISER. Right. So you see the ISER and the IIT logos on top of our, it's there in my background. So Sunil is on the faculty at ISER, and the two institutions in Tirupati have sort of combined their strengths to host the Center for Atomic, Molecular, Optical Sciences and Technologies, CAMOST. Right. So it is jointly hosted by ISER as well as IIT in Tirupati. So Sunil is the program coordinator on behalf of ISER. On behalf of IIT, we have Arijit Sharma. He may be joining a little later. Excellent. So most of the people joining today's seminar might come on the YouTube, because we have a YouTube link. And there may be some coming on Zoom as well. Okay. Well, that's excellent. So this seminar series is enabled also by the G20-S20. Right. Yeah, the S20 is the science wing of G20. And, okay. And this year, India is presiding over the G20. Ah. So that's part of the reason we are having this celebration of sorts. And we made an attempt to get speakers from various G20 countries, including the European Union. So it has not been possible to get a speaker from every G20 country. But we certainly did make an attempt, and we have speakers from Germany, Canada, US, South Africa as well. Excellent. So you have probably you would have received the book of abstracts and
no, I've got it. Right. It's fantastic.
Yes. Yeah.
I mean, this is the talk I'm going to give this morning is, I would say, is a sort of more of a scene-setting talk rather than about my own latest research, though it has some of that in as well. But I just thought I'd try and do a sort of introduction to the area of quantum imaging and set it in some kind of historical perspective. So I hope people will find it interesting.
No, I'm sure it will be very appropriate, because we will certainly have a mixed audience, and there will be people from various disciplines, from science and even engineering. imaging is something which interests a lot of people. So I think we will have a mixed audience. So, an introductory talk will be just appropriate.
Excellent. Well, look, what I'll try and do now is just switch over onto my slides just to make sure that I'm running properly.
Sure.
Yeah, I think there will be several students also attending the talk, so it will
Yes.
be good if it is on the basic level.
Okay, so you should be able to see my slides now, if that's...
Yes,
we can see.
It's a lovely picture.
Oh yeah, thank you. It's the University of Glasgow.
Yes.
Oh, righto.
Yeah.
Do I need to approve that somewhere? I'm looking for the little box that normally comes up. Oh well.
No, I think it is not
fine.
recorded. No, it's okay.
Yeah,
no,
Jaiprakash, everything okay, Jaiprakash, from your
Yes, sir.
side?
Okay, sir. I have started recording also, sir.
Very good.
Thank you,
Okay.
sir. Yes.
So we'll begin in just about 3 or 4 minutes from now. We'll wait another 4 minutes. I can see some people are joining. So yesterday we had the inaugural talk for this seminar series. That was by Professor Arun Pati, the author of the no deleting theorem, as I'm sure you would know. So we just started. That talk is available on the YouTube.
Excellent.
Yeah. And so will yours be.
Fantastic.
So it is time, Miles. Shall we start?
Yeah.
Great. So very hearty welcome to everybody who has joined on the Zoom link, and there are some of you on the YouTube as well, I guess. This is a talk we would have loved to have in person, and I was just chatting with Professor Miles Padgett a little while ago and requested him to come over to Tirupati for a personal visit, when we will absolutely love to have you here, Miles.
Thank you.
So we are really very privileged to have with us today's speaker, Professor Miles Padgett, Fellow of the Royal Society, Kelvin Chair Professor of Natural Philosophy at the University of Glasgow. His work on quantum optics, optical tweezers, demonstration of angular form of the EPR paradox, etc., is very well known. So I'm not going to take much time to introduce him. He is a recipient of numerous awards, just to illustrate a few, and not to mention the most important of those, but let me mention the Lord Kelvin Medal, Science of Light Prize, Max Born Award of the Optical Society, Rumford Medal of the Royal Society, and just a few years ago, he was also appointed Order of the British Empire for services to science research and outreach. So great privilege to have Professor Miles Padgett with us today. He speaks to us on aspects of quantum technologies which impact not only computing, but also communication, imaging, and sensing. So please welcome Professor Miles Padgett. Miles?
Well, thank you very much indeed. And I'm really sorry that I can't be there with you today. So here I am sitting in southern England in the rain and the cold, and I've got my waterproofs with me to go outside after we've given a speech. And so anyway, I thought I'd just start off with an image of my own university. So this is Glasgow University. It was founded in 1450, but in the middle of the 1800s, it was decided there wasn't enough room, and so it moved out onto its present site. And at that time, Glasgow had lots of money, and it built us this rather impressive campus. And this is just one little shot from it, which looks probably more like Hogwarts from Harry Potter than a university, but it's a very nice place to work. And then just more generally, I thought I'd also show you a little picture of Scotland. So this is from my summer holidays this year, out at a place called the Isle of Skye, me and my bicycle. But don't worry, it's not going to be my holiday snaps. I'm going to actually start off with what I'm actually going to try and talk about today. So it's a bit of a historical perspective. It's a bit of where we are now. It's a bit of where we might be going. And the UK, like many other parts of the world, including India, has now a particularly focused area on quantum research, but not just quantum for quantum science, but quantum for quantum technology, and quantum for showing some kind of quantum advantage over classical devices. And I lead one of those activities here in the UK, one of the quantum hubs, and the hub that I lead focuses on imaging. And so that indeed is going to be the subject of my talk today. I'm going to talk about quantum imaging. Many people add an extra word in there, quantum ghost imaging. Why is it ghost? Because quantum is spooky. So essentially, it's just a play on words. And then I'm actually going to talk about whether ghost imaging, such that we know within the context of quantum, is quantum, or is it actually just complicated classical? And then there's sort of a number of different things that one may or may not be able to do with quantum imaging, ranging from resolution enhancement through to improving signal to noise. But I personally think perhaps most important is how one might use quantum science to change the wavelength of the light. And what do I mean there? Well, if I want to image in the visible, I can do that brilliantly well. Here's my iPhone. It has an amazing camera in it with millions of pixels and incredibly low readout noise. it's absolutely brilliant. But it's absolutely brilliant, providing what I want to image is perhaps between 300 nanometers and 1 micron. If what I want to image is outside of that comparatively narrow wavelength range, then my camera technology becomes phenomenally expensive. Even moving into the telecoms band at 1.5, 1.6 microns, a camera, rather than costing 50 cents, would probably be 3 orders of magnitude more expensive. And actually 3 orders of magnitude less sensitive. So a factor of 1 million in that sort of cost performance benefit. And some of that scale, some of it is if people made more of them, they can make them cheaper. But most of it is actually the laws of physics. So imaging at invisible wavelengths is expensive. And I'm going to talk about how quantum science might be a solution around that and show some results, both from our own group and more generally across the world. And so that's basically what I'm going to focus on today. So let's start off perhaps with a definition as to what do I mean by quantum imaging as opposed to classical imaging. Is it really quantum or not? And it would be quite tempting to go through each of these kind of things and then take a vote on whether we regard it as quantum or not. I should say I have quite an open-minded view as to what constitutes quantum. I mean, perhaps at the most extreme, I would say that if you are relying on use of the Hong-Ou-Mandel interference effect, then you are doing something that's quantum. If you are using a squeezed light source, then you are doing something that is quantum. At the other end of the spectrum, there's many, many, many hugely clever classical imaging techniques. Point spread function engineering, where one might use adaptive optics to create strange and exotic point spread functions to give you improved resolution or improved depth of field. Fascinating, hugely clever, probably not quantum. I have detectors that can register the arrival of a single photon, those SPAD, single photon avalanche photodiodes. But actually, even my iPhone camera can nearly see a single photon. Something like the Orca Quest camera from Hamamatsu can most definitely see single photons. Is that a quantum imaging technology, or is it simply quantized imaging? So I'm not going to get hung up over that. And it's probably a discussion for physicists to have while they're out on a walk. In terms of whether it's useful or not, I think that's what we should be focusing on. So that's just a little introduction to my background. Now, here I have made us a cartoon. It is a cartoon showing a nonlinear crystal held in a optical mount. What do I mean by a nonlinear crystal? Well, most optical materials, if I apply an electric field, then the electrons sort of displace themselves slightly within the crystal. And that displacement or polarization, as we would call it, would be proportional to the applied electric field. If I have a nonlinear material, then there's higher order terms. Some of that polarization of the optical material means that if I apply an AC field in particular, then I'm going to get harmonics of that AC field exhibited in the polarization. And therein lies the heart of a nonlinear optical material, where, for example, I might choose to illuminate that nonlinear optical material with a very powerful and intense infrared beam at 1 micron. And that nonlinearity means that the emitted light from the material is no longer infrared, it's in the green. And in essence, probably virtually every green laser that you've ever seen is not actually a green laser. It's an infrared laser, which is then frequency doubled into the green. And that would lead us into a whole area of nonlinear optics. Incidentally, also a way in which one can transform the wavelength of a light beam from the infrared into the green in this case, albeit not usually with very much efficiency. However, that whole process works back in reverse. I can take green light into the crystal and out pops not green light, but also some infrared light. Now, energy is conserved. So if I look very carefully at the level of individual photons, then if I take, and now here comes my cartoon, if I take that crystal and shine into it an ultraviolet photon, what I can get out is not an ultraviolet photon, but 2 infrared photons. Energy is conserved so that the frequencies of those 2 infrared photons adds up to give me the frequency of the ultraviolet photon. Momentum is conserved. If one of those infrared photons moves off slightly to the left, the other one moves off slightly to the right. Angular momentum is conserved. Time is conserved. Both of those infrared photons come out at the same time that the UV photon went in. And these conservation rules are correlations. They give rise to correlations. And actually, although not the subject of this particular talk, when I have situations where both the momentum is conserved and the position is conserved, that raises all kinds of interesting questions relating to the uncertainty principle. And therein lies the heart of quantum entanglement. And that is why sources such as this are of such interest to the quantum community, because these conservation rules apply to conjugate variables like position and time, position and momentum, or energy and time, or indeed different bases of polarization. Now, this process where a high energy photon can give rise to 2 photons of lower energy is called parametric down conversion, or spontaneous parametric down conversion, SPDC, and you may have seen those initials in papers. Now, these photons, just for future use, have names. I'm tempted to call them Tom and Jerry, but I won't call them Tom and Jerry. The incoming photon is called the pump photon, and the 2 photons that are emitted are called the signal and idler photons. And I merely introduce that vocabulary such that when you read papers on the topic, you can understand it, but also because I will probably end up slipping into it by accident in the rest of my talk. So, the signal and idler photons, those are the 2 photons that are emitted, are correlated to each other. They're correlated in the terms of their number. 1 pump photon in gives exactly 1 signal and 1 idler photon out. The time is correlated. That means that if the pump photon comes in at 12 o'clock on the Tuesday, the signal and idler photons come out at 12 o'clock on the Tuesday. Their frequencies are correlated. If the signal photon comes out a little bit red, the idler photon comes out a little bit bluer because energy has to be conserved. I've already mentioned that the momentum is conserved. If one photon comes out a little bit to the left, the other one comes out a little bit to the right. There are also more subtle things that are conserved. If one photon comes out slightly divergent, let's say in terms of its phase front, so it's spreading, the other photon comes out slightly convergent, so that it's being focused. Incidentally, that correlation of phase structure is why the signal and idler photons are correlated in their orbital angular momentum. I won't go into that as a subject for today, but I'm sure many of you know it's a subject that's close to my heart. So I'm now going to talk about how we might use some of these correlations to do, at least in principle, useful things. And so I'm sure many of you are familiar with the film character Batman. I tried to do a Batman accent there and failed, but you know the one I mean. And those of you that are familiar with the Batman comics or Batman films will know that when the police commissioner in Gotham City has a problem, that he doesn't phone Batman or FaceTime him. He shines into the night sky a projection of the bat signal, and Batman sees the bat signal in the night sky and then comes to the rescue. And so I would like to think now and talk a little bit now about how do I do that in a way that only Batman can see the bat signal. I don't want the Joker or the Riddler to see the bat signal. I only want Batman to see the bat signal. So let's think how I might do that using quantum. So now I've got another, again, a cartoon here, and I hope that you're going to recognize the building blocks within it. So we have our nonlinear crystal on the left-hand side. I'm going to woggle my mouse over that just so we can see where it is. Hope that you can see my mouse. And then we have coming into that, my ultraviolet photon. That ultraviolet photon gets split to form 2 infrared photons. Now, it's a little bit like, you know, listening to clicks on a Geiger counter. If I shine light in a light beam, and the photons arrive at my detector, and those photons arrive at my detector, and my detector goes click every time it sees a photon. What would I hear if I shone on my light beam at my detector? It's tempting to think I would hear like a metronome, click, 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 click. But of course, that isn't how light, even from a laser, behaves, because the temporal distribution of the photons is subject effectively to Poissonian statistics. It gives rise to shot noise. So on average, I might receive 100 clicks every second. In the next second, I will receive 100 clicks plus or minus the square root of n, or that's the standard deviation over which I will see. So in 1 second, I might get 100 clicks. The next second, I might get 103. The next second, I might get 94. The next second, I might get 100 exactly. Who knows? And those photons come along effectively with Poissonian statistics at random time. It's a little bit like radioactive decay. It's the same kind of thing that you would hear on your Geiger counter. It's a random event. So I know I'm going to roughly get 100 photons a second. I don't know precisely at all when those are going to arrive. And so the photons that come down this lower channel are going to come in some kind of random time sequence. And that random time sequence is effectively, I'm going to say, known only to the source. I've got no way of controlling that. It just is what it is. And so this will give me at the detector here a random time sequence. The top photon, I've got a lens, an optical system. It's going to, I've got the BAT template. This is still in Batman's space. So sorry, in the police commissioner's space. And those photons now, one by one, are going to arrive at my camera. And I will see those photons arrive at the camera one by one. And eventually they will arrive in sort of different places. And eventually they will build up the symbol of the bat symbol. However, what I also do is deliberately now add a source of background light. Of course, in the real world, I don't need to deliberately add a source of background light. The real world carefully provides me with a source of background light. It's called the sun or the moon or the street lights or who knows what, but there are photons flying around all the time. And so unfortunately, if all I have is my camera, then not only do I get the photons that are the bat signal, I also get lots and lots of photons that are not the bat signal. And so if all I have is my camera, I end up with a very bad image. But if I'm clever with my camera and use this secure link at the bottom to essentially open and close its shutter, because the bat photons will arrive at exactly the same time as this random sequence, then I can separate out the bat photons from the background photons. And so here actually is a paper that we published earlier this year, where we did exactly that. We used a gated camera. So what do I mean by gated camera? It's a normal camera, but in order to see these single photons, it has at the front of it an image intensifier. That image intensifier switches on and off very quickly so that the bat photons are amplified and the background photons, which arrive at slightly different times, are not amplified. Now, if there's no background light, then the ungated image and the gated image effectively look the same, because all the photons are back photons, and as long as I just keep the shutter open, I'm going to do just fine. When I start adding background light, however, you can see here that the ungated image effectively becomes invisible, where the gated image is still recoverable. And so the only person that can see the back signal is the person that also has the secure link. We might think about how one might make that link secure. It could be a technological security in that it's a buried optical fiber. Of course, someone could listen into that. Someone could dig up the fiber and eavesdrop us. Well, that secure link could also be quantum cryptographically encrypted, such that I can detect the presence of someone meddling with my link. So not a rocket science example, but nevertheless, a simple example of how one might use quantum time correlations to secure or protect, in this case, an image. So the obvious question is, can we use other correlations, or how might we use other correlations? So let's look at those correlations more carefully. If I imagine that my crystal is big, let's say it's several millimeters across, and I illuminate that crystal with a big pump beam, then in a sort of not quite the correct sense, but it will do for now, in that big pump beam, some of the photons in the pump beam are at the top. Some of the photons in the pump beam are at the bottom of the beam. Some of the photons in the pump beam are at the right-hand side of the beam. And what happens is the position of both the single and idler photons matches the position of the pump beam. So if I look very carefully at this crystal, I will see that it keeps on generating pairs of infrared photons. Sometimes that pair of infrared photons is at the bottom. Sometimes that pair of infrared photons at the top. Sometimes it's the left, sometimes it's the middle, sometimes it's the right. And so when I look very carefully at the crystal and I see these photons arrive one by one, I would see something like this. That the signal and idler photons, although when looked individually, are scattered randomly over the beam cross-section, if I look at both the signal beam and the idler beam, I see that pattern is the same. In this case, it sort of looks like a little star constellation, but it's the same. That would not be the case if I took two laser beams of equal power. I might get the same number of photons in the two beams, but they would not have the same precise position within the two beams. The only way that I can get this same precise position of the photons within the beam is by using this parametric down conversion source. So here, as well as having the temporal correlation, i.e. the photons arrive at the same time, I see now that if I look more carefully, the photons in the beam arrive at the same position. How might I use that to do imaging? Well, the answer was first proposed by Yanhua Shi and co-workers. Here, this is a paper from 1995, and it is the paper that gave, I think, rise to the concept of ghost imaging. Now, the paper title is Optical Imaging by Means of Two-Photon Quantum Entanglement. Is it quantum? Maybe not. Let's see. But it's certainly a new, or was a different way of imaging. So let's look again now at what we have here. Here we have, again, the same kind of cartoon you recognized before. I have my two photons that come out at the same time and the same position. I have my object up here, and I have some kind of imaging detector at the bottom. That imaging detector can measure the position of the photon. At the top, however, I don't have a camera. I simply have a large single detector, and all that large single detector does is tell me, did the photon get transmitted by the object, yes or no? So the photon comes along, and I just have up here a whole stream of yes and no's, I know nothing about the object. All I know is how transmissive it was. Half the photons got through. Okay. What did it look like? I have no idea, but I know it was 50% black and 50% white. On the other hand, at the bottom, I've got the position of every photon, but I don't know whether the photon got through the object or not, because the photons at the bottom never went to the object, they just went straight to the camera. However, clearly, if I combine those two pieces of information, then I say, where was the photon? Did it get through? Where was the photon? Did it get through? If I look at the AND operation between those two detectors, or the coincidence count between those two detectors, I can recover the image. So I can only recover the image if I have access to both detectors. Similarly, I am recovering the image of photons of which I never measured the position. I measured the position of the other correlated photon. Now, this, you can see now why it's called ghost imaging, because it seems to be action at a distance. Now, the trouble is with this scanning detector of the original work, that actually most of the time the detector's in the wrong place. You've got this scanning detector, but who says the photon is going to go where the detector is? Most of the time it misses. And so it's a massively inefficient use of light. It's a massively slow system. And so one thing that we did, actually working with Bob Boyd's group in Ottawa, was change that single pixel detector to a single photon camera detector, which can measure now the photon at any position. And this is the intensified camera of which I've spoken already. This particular one was one made by Andor with the image intensifier in front of it. And indeed, we're not the only people to try using cameras in quantum experiments. And here are a range of papers that I think are really great, mainly from other people, which are worth a really good read. I won't go through them each in turn. So we replaced the scanning detector with a camera. Trouble is the camera is a bit slow. And so we actually had to put a delay line in front of it. As in, when you tell the camera to take a picture, it does nothing for about 40 nanoseconds, and then it takes a picture. So you have to delay the image by 40 nanoseconds. We did that with a series of mirrors. Looks rather complicated. It is indeed rather complicated. This was a specially cleaned optical table to take a picture. But here we go. And here are the cameras. Here are the gated images, the photons arriving at the camera. None of these photons saw the object. They all went straight from the source to the camera, but the camera only took a picture of the photon if its correlated photon was transmitted through the object. So the detector measuring the transmission or not had no pixels. It was just effectively saying, take a picture now or don't take a picture now. So if I remove that cable, I would just get no information here at all. It would just be every photon ever sent. But because I have that cable in place, you can see that I'm picking up here. In roughly speaking, this is not accelerated data. This is the speed of the data coming in. So a few seconds allows me to build up an image of the object. So the question now, perhaps, is that a quantum effect? It's certainly interesting. It's certainly spooky, but it's probably not quantum. Why not? I'll explain. So this is what we have. Now I've drawn this now in a little bit more detail in that I've actually put the lenses in the right places. So I've got my crystal here. I image the photon from the crystal onto the object. I image the other photon from the crystal onto the camera. The photon in the object and the photon in the camera are in the same place because I'm relying on the fact that my photons were position correlated at the source. And therefore, they were in the same place at the source of the crystal. They're in the same place at the object and the image. Okay, fantastic. But also I could have done something different. I could instead have gone into the far field of the source. And now, because if one photon in momentum goes up, the other photon goes down. If one goes right, the other one goes left. The relationship between my object and the recorded image is namely that of an inverted image. So the photon that goes through the eye socket at the top effectively the other photon is going in a direction corresponding to the eye socket at the bottom, because it's momentum correlated, it's anti-correlated. So depending on whether I have the lenses set up like this, or I have the lenses set up like this, my image that I record on the camera should be inverted or upright. This is an upright image, it's in imaging speak. Now, we can do that, and indeed, we did do that. Here's a nice paper using the same system as before. And you see that by relying on the momentum correlation in the down-converted pairs, I've got an upright image. Whereas if I move the lenses to rely on the position correlation gives me the upright image. If I move then the lenses to give me momentum, I get an inverted image. And what we've shown here is that the system is both correlated in its position and correlated in its momentum. Actually, the precision of the images is such that the delta X blurring or resolution in position multiplied by the delta P resolution in the momentum image, when I take the product of that, I get a number which is less than h bar over 2. I sort of worry that somehow I've done something which is in violation of the uncertainty principle. And what I'm doing here is showing you essentially an image manifestation of the famous Einstein-Podolsky-Rosen paradox. So I would argue that although any one of these images on its own simply shows correlation, the fact that I can take either image demonstrates correlation in complementary bases, and therefore is a demonstration, albeit not loophole-free, of the Einstein-Podolsky-Rosen paradox, and therefore, I would say, is relying upon a quantum effect. What I would also confess, however, is that I cannot think of an application where being able to go from an upright image to an inverted image is really very useful, beyond the sort of security protocol. Because actually, if I wanted an upside down image, I could take the image into Photoshop and simply say, flip the image. So there's easier ways of producing an image which is upside down than switching the correlation of the quantum source. So I would say the effect is based on a quantum effect. However, from a usefulness point of view, if quantum was sort of different, it would be sufficient simply to have a position correlation or a momentum correlation. Now, I want to just introduce a little bit of sort of, these things seem very difficult, and they're actually not as difficult as I've perhaps made it sound, and I apologize. I'm not trying to overcomplicate the subject. So how can one predict the outcome of this type of experiment? Now, clearly, I could sit down and I could learn lots about quantum mechanics, and I could maybe predict some kind of outcome, and it might or might not be a correct prediction. So I'm now going to talk about the completely equivalent classical system. How could I use classical optics to predict the outcome of a quantum experiment? So here's another. This is not a quantum experiment. It's a classical experiment involving lenses and light sources and mirrors. And I just want to look at that, and I'm going to go back to this. Okay. Remember that image. I've got an object. I've got the lenses, and that object and the crystal are imaged onto each other. I've got the crystal, I've got some lenses, and I'm imaging that image back onto the camera. Here, I've got an optical layout which looks actually the same, other than my nonlinear crystal has been replaced by a mirror, and my bucket detector, that detector I had behind the object to measure whether light was transmitted or not, has been replaced by a light source. So photons leave the light source, they go through the object. I form an image of the object actually in the plane of the mirror. That image is reflected by the mirror, and it is re-imaged from the mirror onto the camera. And in this instance, I have an upright image. I'm just going to go back again and say exactly the same thing, but with the wrong diagram. A photon leaves the bucket detector, goes through the object, is imaged into the crystal, where it is reflected from the crystal and is imaged onto the camera. All these things are in the same physical position. The only thing that's changed is the direction of light. So in this quantum experiment, both photons leave the crystal at the same time, and they arrive at the bucket detector and the camera at the same time. In my classical picture, the photon leaves the light source, at some times later hits the mirror, and at some time even later than that hits the camera. What's changing here is the time ordering of events. And now when people talk about quantum experiments and talk about coincidence counting, they're talking about time synchronization. When they're talking about coincidence counting between two detectors which are separated by a large distance, they're talking about essentially coincidences, out with the space-time cone. They're talking about non-local coincidences or spooky action at a distance coincidences. The strange thing is not the result. There's plenty of things that give me a result. The strange thing is the time ordering. So here I've got my light again. My photon leaves my light source, hits the mirror, then hits the camera. I'm going to do a different system. Oh, I've changed now my lenses so that my object and mirror are in the far field of each other. This again is exactly analogous to the quantum experiment. And now I've got an inverted image. And so I can both get upright and inverted images by changing lenses in the classical world, just as I could do in the quantum world. And so now I bring all of those things together. On the on the top row, rather, we have the quantum experiment where both photons leave the crystal at the same time and arrive at my two detectors at the same time. I can get upright and inverted images. I now replace my crystal with a mirror. I replace my bucket detector with a light bulb. I get exactly the same images, but the time sequencing is different. My photon leaves the light source, at a later time hits the mirror, and at a later time hits the camera. So, and the images you have in the middle there are real experimental results from our real thing. And actually, I never replaced the crystal at all. I kept the crystal in place. Luckily, the crystal has a facet which reflects light. So my nonlinear crystal is also a mirror. I don't need to change it at all. The only thing I needed to change was the bucket detector. And hey, that was fiber coupled. So I simply unscrewed the SPAD detector and screwed on in its place an LED. And then just ran the experiment again. And I get the same images on my camera. Incidentally, just out of interest, you see in the momentum configuration that the images are not quite in the same place. They've been displaced slightly. That's because the front facet of my crystal was actually at a slight angle to the optical axis of the crystal, so that my mirror was working at a slightly different angle than my down conversion source was, and hence in the far field you get a slight displacement of the image. So this is sort of this idea of using classical concepts to predict the outcome of quantum experiments is sometimes referred to as either sort of back projection or retrodiction. And actually, it doesn't just apply to quantum experiments. I mean, the Bell inequality, whereby you measure the coincidence counts in the Allen assay by looking at the rotation or the relative rotation of two polarizers, is exactly what you would see in Mauss's law. If you shine light through one polarizer and then shine that light through a second polarizer, and then you rotate the polarizers, you see cos squared fringes. And now in the quantum experiment, the light source starts off in the middle and goes through both the polarizers at the same time. and you look at the coincidence counts, what do you see? You see cos squared fringes. The results are the same. The thing that's different is the time sequencing. And that's why all these loopholes with separation, rapid response detectors, that's why that was essential to demonstrating the non-locality of quantum mechanics. It's not the results, it's the non-locality that's strange. How might it be different? I did already allude to the fact that I see there's a question in the chat box. Will the left-hand side become the right-hand side? Yes, the whole image is flipped. Everything's reversed, X and Y. I've already alluded to the fact that if one of the photons comes out a bit red, the other one comes out a little bit blue. Well, I can really go to town on this because I can come in with my UV photon at 355, and rather than getting two photons at 710, I can get one photon at 1.5, 1.6 microns, and the other one at about 500 nanometers. And now I can illuminate my object in the shortwave infrared, where my camera is rubbish, and yet I can record the position of the blue-green photon in the visible, where my camera is brilliant. What do I mean? I mean this. My UV photon comes in, my infrared photon goes off to the object, through which it may or may not be transmitted. My visible photon goes off to the camera, where its position can certainly be recorded. And then doing that, I can effectively, in this case, I'm showing you results of looking through a silicon wafer. So the infrared light, the silicon is transparent to the infrared light. The infrared light goes through. We've got some metallized pattern on the wafer, which of course blocks even the infrared light. And yet the light I pick up on the camera is in this case at 460 nanometers at the peak of the photocathode response. And so this is an example of a wavelength transformation where I have used the infrared properties of the light to probe the object. And yet I've used the correlated visible photon to have a highly efficient camera record those photons one by one. And people say, well, what's the efficiency of that? Every single infrared photon that I use to illuminate the object has exactly one visible photon equivalent. It's not a conversion efficiency of 10 to the minus 7. One infrared photon gives me one one visible photon. Now, it is true, I had an inefficiency in their generation. I had lots and lots of UV photons, and only some of them gave me photon pairs. But that's fine, UV lasers are cheap. What's important is I got exactly the same number of infrared photons as I had visible photons. And so that leads to a highly efficient system. So there is one use of quantum technology, using the quantum correlation to allow me to have an infrared illumination and a visible detection. Is there a better way of doing it? Yes, there is a better way of doing it. Sadly, not a way I thought up, a way that somebody else thought up. And it's this wonderful paper, wonderful, wonderful, wonderful paper, inspired by other wonderful papers, as so is often the case. Most wonderful papers rely on other people's previous wonderful papers for some part of the idea, and this is no exception, and certainly that's the way science is meant to work. It was a paper published in 2014 by Anton Zeilinger's group, and in particular, Gabi Lemos, who was a PhD student with Anton at the time, working with Sven Ramlo, also one of the postdocs in Anton's group at the time. And it's this paper in Nature called Imaging with Undetected Photons. I'll talk about it now. It was inspired by work of Leo Mandel in 1991, and then other people have gone on to use it and done great things subsequently, not least Sven Ramlo himself with this amazing paper in Science Advances, which was published in 2020. How does imaging with undetected photons work? Well, first of all, I'm going to describe how you can do imaging with an interferometer. So here's a classical interferometer. It's a bit strange. I've got an incoming beam splitter, an outgoing beam splitter, but I've added in lots and lots of lenses so that everything is imaged onto everything else. So that incoming beam splitter, and you see that what I've done is I've replaced one of the mirrors with my object. So you can think of that object at the top as being a mirror, but a mirror where only part of it is reflective. Imagine I've got a mirror and I put in front of it just a transparency. So what would I expect to see in that instance? Well, I've got light in the two arms. It comes back together at the beam splitter, and I get interference after the beam splitter. And I get constructive interference, I get destructive interference, but I only get interference where I have light in both arms. If I put my hand in one of those arms and block one of the beams, I no longer get interference. Pretty obvious. So now the beam splitter, I want us to think a little differently about beam splitters. One way of describing a beam splitter is that light comes in and half of it goes one way and half of it goes the other way. Well, that's true, but it's not the interesting bit. I think the interesting bit with a beam splitter is that the beam splitter maintains a phase correlation between all of the light beams. The light comes in with a phase, the transmitted light has the same phase, and the reflected light has the opposite phase. There's a relationship between the phase of the two output beams. And without that, interferometers wouldn't work. It's the phase, it's the fact that beam splitters maintain phase that is interesting. Now, so I've got a device here, which is called a beam splitter. I've got three beams here. I've got an input beam and two output beams. And this beam splitter magically maintains the phase relationship between the three beams. But other things do that too. In fact, our nonlinear crystal does that. If the phase of the signal is a little bit advanced, the phase of the idler is a little bit retarded. And they're both driven by the phase of the pump beam. So I now replace my beam splitter with a nonlinear crystal. That nonlinear crystal needs a pump beam. That's my pump beam coming in. You can see my UV photons. And both of those nonlinear crystals produce my signal and idler output beams. In this case, my signal beam is in the visible. My idler beam is in the infrared. My infrared beam goes off to my object. The infrared beam and the idler beam come back again. And everything still exhibits interference because I've got this phase relationship. And so in a nonlinear interferometer, such as this one, the interfering beams, and it sounds counterintuitive, the interfering beams are not the same frequency. They interfere through the nonlinear interaction in the nonlinear crystal. And I see interference in the output. I see interference, the infrared light interferes with the visible light. And so I see interference, in this case, in the blue beam. And the blue light interferes with the infrared light. And I see interference in the infrared beam. However, I don't need to look at the infrared beam. The interference is there anyway. I can just look at the visible beam. And so the visible beam, I see this interference pattern. But it only exists because the infrared light has struck the object. And so the pattern that I apply to the infrared beam is picked up in the interference pattern and is therefore visible in the visible beam. So when Anton said in his paper, I've done imaging with undetected photons, well, he has imaged with the infrared light, but he never measured the infrared light. He relied on using that infrared light to interfere with the visible light, and he measured the visible light. So although we imaged without detection, it's important to stress here that we did not image without illumination. The object is still being illuminated. It is just not being detected. Now, this, I think, is a wonderful, wonderful technique. Full credit to Anton and his group. We can now have an argument about whether it's quantum or whether it's simply nonlinear optics. That's an interesting discussion to have, but none of that discussion to take away from the fact that this is now a brilliant technique, because I can illuminate in the infrared and I can image that information in the visible with my super cheap, super wonderful camera. And one of my colleagues, Chris Phillips, at Imperial College London here in the UK, as his student Emma Pierce, has built a wonderful little demonstrator of this technique about the size of a large book, which contains the laser, the nonlinear imaging crystal, the object and everything, imaging in the infrared with a webcam. Wonderful technique. So those are the papers. I'd really recommend that you take a look at them. Now, I've just got a few more minutes, if I may, and I'm just going to whiz through some other effects. And so this is a great paper. This is a paper from Seth Lloyd, quantum illumination, turn-to-phase quantum illumination. What was he talking about here? Well, you recognize this picture now. The reality is, although I get the same pattern in both beams, I also have all the background light. I also have noise on the camera. So the correlation doesn't really look that good. Any low photon image I recover also has lots of noise. But here, I can distinguish the noise from the real photons because the real photons appear in both images and the noise does not. How might I use that? Well, here's a wonderful example of a paper by Breda and co. doing exactly that. I separate up my identical photon pairs, and I've already mentioned that I have shot noise. However carefully I make an imaging system, if I do it and I've got 7 photons in the pixel, the next frame is going to have 7 plus or minus √7. I'm going to have the shot noise. But the shot noise is the same in both of those images. And so when I subtract them, I go from having the classical image here, a rather noisy pi. I subtract the matched noise, and I end up with a wonderful pi. We did something similar. This is a paper we published in 2020, whereby deliberately now adding in thermal light. So I've got my quantum illumination source on the left-hand side. It gives me that sort of random distribution of photons. All of these photons are real. I then illuminate my object. I record that image on a camera. But here, I deliberately added in noise. I deliberately added in noise. In this case, it wasn't just noise, it was a false image. And so I've put a cage on top of the bird. But if I run an AND operation between this classical image and my quantum reference, I can recover the quantum image all on its own and extract the image from the noise or extract the image from the false image. And here is some experimental results doing just that. This is on the left-hand side, what the camera actually sees. It's a bird just trapped in a cage. The cage is very bright. I can't see the bird at all now. But when I recover and run that AND operation with the real photons, I can extract essentially the bird image against the noise. And so I can use this spatial correlation of the photons to suppress the background light, remove the false image. I can also do something in relation to resolution enhancement, and I haven't really sadly got time to cover that, but I'll just, they'll be in the slide deck that I distribute after this talk. What I really wanted to do was just finish up is what more can quantum do beyond correlation? And I mentioned the Hong-Rou-Mandel dip before, and this is the Hong-Rou-Mandel effect, whereby I have my down conversion crystal, I produce my 2 infrared photons, they meet again, this time now at a beam splitter. And whereas in classical physics, I'd expect each of those photons to make up their own mind about which way to go. So they've each got a 50-50 chance. Sometimes they go the same way, sometimes they go different ways. In quantum physics, because the photons are bosons and indistinguishable, they always go in the same direction. And that is known as the Hong-Ou-Mandel dip. And it tells me that these two photons arrived at the same time. And because I can do same time discrimination, it means I can also do depth. So if one of those mirrors moves, then they no longer come out at the same time. They no longer go the same way. If I've got relief features, i.e. contours on that mirror, then some parts of the image, they'll come out at the same time. Some parts of the image, they won't come out at the same time. And my colleague in Glasgow, Daniel Padgett, has essentially used that as essentially to make a depth-sensitive microscope. It's sort of the equivalent of optical coherence tomography, but in the quantum regime of single photons. Here's another example of Warwick Bowen, Brisbane University in Australia. And I mentioned right back at the beginning of using squeezed light, suppressing the shot noise in a fluorescence microscope, in this case, to take exquisitely sensitive images at extremely low optical power. And in this particular nonlinear microscopy paper, demonstrating that it can surpass the signals and noise of a classical system. So what do I think? This is my conclusion slide. I think the non-local correlations, well, we can use them. There's no question that we can use the temporal correlation, the momentum correlation, the position correlation, the orbital and angular momentum correlation to do many fascinating optical experiments that recover images. And that those experiments can show improved signals and noise. They can show improved resolution. They can show improved sensitivity. I might, in my darkest moments, worry that it's a lot of effort to go for a system that's only slightly better than the classical system. And I would say where I have no doubts, and where I think personally the most promise lies, is not in the 3 dB of extra resolution or the 3 dB of better signals to noise. I think it's the wavelength transformation, which I've gone to some lengths to try and explain. Because I think with the wavelength transformation, we're not talking about 3 dB. You're talking about making the impossible possible. You're talking about, I can now do infrared imaging with my iPhone camera. I can now do X-ray imaging maybe with my iPhone camera. I can now maybe do terahertz imaging with my iPhone camera. Now, the X-rays and the terahertz is still a technical challenge which no one's yet shown. But people have shown that I can go into the shortwave infrared. Sven Ramlo and colleagues has now got out to about 6 to 7 microns, again, with a silicon camera, and doing some very interesting life science microscopy in the mid-infrared spectral region, but still using the highly, not just cheaper, but 100 times, 1,000 times more sensitive silicon technology compared to all these exotic infrared cameras. So I think that's a really exciting area. So thank you very much indeed for listening to the talk. I went on for a little bit longer than I intended to do. I'm really sorry about that. If we don't have time for questions, I apologize. If we do have time for questions, I'm happy to stay and answer some.
Oh, not at all. It has been such a fascinating talk, and I'm sure the audience would have loved to hear you even more. And it's amazing how much you can achieve pushing the limits of classical physics and also recognizing what exactly and where the quantum effects are and where they are not. So this is really an amazing talk. I'm sure there are some questions. Let me request Sunil and Abhi to help us with the question answer session. Sunil, do we have some questions?
Yeah. I think right now, maybe those who are listening to the talk can unmute themselves and ask questions. And there are 2 other questions I'll just read out probably after this. Or maybe I will start with that questions from the chat.
Yeah, go ahead.
So there is a question from Dr. Srabanikar. Do the optical path lengths on upper and lower channel affect the gating?
Yes, so I have to gate at the correct time to see the photon. So if I'm going to use these kind of gating approaches, I have to understand the path lengths of the two arms. And that's really just the same as you would do in any, like if I take a Bell experiment, then, you know, when I talk about, you know, looking at coincidence counts, you better hope that both of your detectors are exactly the same distance away from the source. And if they're not the same distance away from the source, then I need to allow for that in my coincidence counting. Okay. Now, that is both a blessing and a curse. It's a curse because I have to get it right. It's a blessing because, of course, it makes my data now depth sensitive and so allows me to do 3D imaging because I can sweep the gate time and I can recover, therefore, you know, images corresponding to different depths. So that's interesting. By the way, if I may, I misspoke in answering the question that someone put in the chat while we're going along. Someone put in the chat asking me, you know, I've shown you that the image is inverted up, down. Is it inverted left, right? And I said yes. I wish I hadn't said yes, because what I'm talking about here is essentially a mirror inversion. And it's like one of those, it's that question that I still struggle desperately with, which is why is it when I look at myself in the mirror, my left and right hands are interchanged, but my head and my toes are not. And let's not get into answering that question because we sort of all understand why, but it's always so difficult to explain. So it's exactly the inversion that one gets in the mirror. That's what I really wanted to say. And now we can talk about whether up and down and left and right mean the same thing or different things. And I think it says a lot about the symmetry of our bodies that we get hung up in the language that we use about mirror inversion, in that my head and my toes look much more different from each other than my left hand and my right hand. Anyway, sorry about that. So next question.
Okay, thank you for your explanation, Professor Miles. And there is one more question from Dr. Sravanikar. What crystal was used? What is the efficiency? What is the efficiency? Yeah, efficiency, the SPDC and emitted correlated photon.
Yeah, no, that's a really good thing. Let's go back to one of those just to talk through the kind of efficiencies in you know, if I have an experiment that looks like this, what kind of power levels, what kind of efficiencies might I be talking about? So I'm just going to talk about you know, our own experiments. And so I might start off with a UV laser here, which is a CW laser, let's say 100 milliwatts. I probably have a 3mm diameter beam. I probably have a 10mm diameter crystal, which is a millimeter thick. And I haven't spoken about the effect of crystal thickness and the like, and these things are really important in terms of the field of view and the resolution, but a discussion for a different day. So I've got my 100 milliwatt beam coming into my 1mm thick crystal. And I'm probably going to generate photon pairs. I'm going to generate photon pairs. And I'm going to be generating photon pairs at, you know, tens of thousands of pairs every second. Sounds a lot, but it's clearly an extremely small fraction of the UV photons that came in. And so my conversion efficiency from the UV into the infrared, it might be 1 in a million, might be 1 in a billion. I mean, tiny conversion efficiency. But the rest of the UV light just goes through and you absorb it in a little beam stop somewhere and it's never seen again. What's important is that for every single signal photon I generate, I've also got an idler photon. So these are perfect photon pairs. Now, those photon pairs go off to my bucket detector and my camera. My bucket detector, which is, let's say, non-spatially resolving, depending on the wavelength, but probably has an efficiency, a click efficiency of 60–70%. So it will register 60 to 70% of the photons. If I move to my camera, my camera efficiency, in the case of an image intensified camera, my camera efficiency is probably around about 5%. So my camera is told to take a picture and 95% of the time it fails, 5% of the time it succeeds, and I get that photon. So not great. Now, if I change the camera technology to an electron multiplying camera, then my quantum efficiency can be as high as 80%. I've done lots of experiments with EMCCD cameras. I'm not talking about them here. You lose the time resolution, but you get back the efficiency. The latest generation of CMOS cameras from Hamamatsu, I've mentioned them already, these Orca Quests. I'm going to sound like an advertising person for them. I don't mean to, but they're simply remarkable. They count the number of photons in each pixel. Wow. You know, you go, oh, that pixel had 4 photons in it. That pixel had 1 photon in it. That pixel had no photons in it. You're now down at the level that CMOS technology, similar to what's in my phone, being able to count the number of photons. And incidentally, I have every confidence that in 10 years' time, the camera in your iPhone will be counting the number of photons in each pixel. And you think about the transition from traditional photography, it is absolutely unreal. Your iPhone camera has an effective ISO film rating, you know, orders of magnitude better than a traditional 35mm film camera. I mean, you know, they take pictures at nighttime, not by accident, but by exquisite sensitivity. And I mean, the effective readout noise of an iPhone camera is probably 2 or 3 photons per pixel, and, you know, getting better all the time. So clearly, I call it an iPhone camera. The cameras are made by somebody else, but purchased in volume to go into your iPhone. But that silicon CMOS technology is just incredible. And I think really we could do a lot worse as quantum opticians by asking ourselves, how can we combine the cleverness of quantum science with the absolutely amazing advances being made in consumer technology?
Okay. Yeah, I think maybe is there some other questions from other audiences? So you can unmute and speak.
Check if there is anything on the YouTube.
Yeah, that's what I have read.
Okay.
Dr. Srabani had sent it in the YouTube. So is there anyone else?
Yes.
Okay, Professor Miles, I just have some simple question. So you had said that your Beckett detector had a fiber coupled detection, right?
Yeah.
So this efficiency which you were mentioning was including that efficiency of the fiber coupling, or?
Yeah, no, that's about right. And incidentally, I mean, you can do again a discussion for another day, but in terms of the bucket detector, you are using multi-mode fiber, of course, because I want essentially the fiber to pick up the whole image.
Okay.
But you can also ask, what happens if I use single mode fiber? And essentially, in a quantum sense, those questions are quite difficult. But when one moves through to the sort of the classical equivalent, you ask yourself exactly the same question. You know, I've got my light source here. That's multi-mode. Alternatively, I could take my light source and pass it through a very small pinhole, at which point it becomes single mode. And then the same kind of changes that you get in a microscope by going from essentially a multi-mode illuminator to a point source illuminator is exactly the kind of changes you then see in the quantum system as you go from a multi-mode bucket detector to a single mode bucket detector. And again, what would have seemed, at least to me, to be quite a complicated quantum question. Oh, how does the ghosted change if I change the multi-mode fiber to a single mode fiber? Actually, when you think about it in the classical equivalent, becomes sort of trivial, because you're just switching from an extended light source to a single mode light source in terms of your microscope. And of course, microscopists do that kind of thing all the time in relation to phase contrast microscopy. You know, if I'm going to do phase contrast microscopy, I'm going to put filters in the system. then I often spatially control the spatial coherence of the source. And again, we've done all of that essentially in the analogous quantum case of showing that effectively those things that one would think of doing in classical microscopy also have exactly the same effect in the quantum case.
Oh, okay. Yeah, thank you very much for your explanations, Prof. Miles. Is there any further questions?
Yeah, I think it is about time. So
Yeah, I think
so,
then let's
so if there are
conclude
some more
the
questions.
session. Yeah.
I think they should email or something.
Yeah, no. I'm busy for the rest of the day, but I've got a train journey later this evening. So if anyone emails me a question, I will do my best. I will do my best to answer it in about 6 hours' time.
Yeah.
Sunil?
Yeah, sir. Yeah, I think now I don't see anyone else. So there is also no questions from the chat. Maybe somebody can write an email and then we can send it to Professor Miles. Yeah.
Thank you.
Yeah.
So thank you very much indeed, and I wish you all the best with this seminar series. It's a fantastic thing to have done, and thank you for giving me the opportunity to talk about some of the work in the world in quantum imaging.
Yeah, thank you very much, Professor Miles. It has been an illuminating talk, actually. So in terms of the presentation and the presentation style, especially the students would have benefited a lot. And we will also be uploading this and keep it as a record in the YouTube, so they will be able to watch it, those who could not actually attend, because this is actually a time where many students have classes. Unfortunately, they are not able to attend, but they will be able to see this talk in the YouTube. Yeah. Thank you very much. And I would like to thank also the participants who is over here. And in addition to that, the whole thing was organized with the help of members from the CAMOST team. And I would like to thank all the people who have helped to organize the event. And yeah, mostly I think I would thank you for accepting our offer and presented the talk in this.
Thank you very much.
Thank you.
Thank you. Bye-bye.
Yeah, yeah.
So thank you very much, Miles, and goodbye for now. We look forward to having you in Tirupati sometimes.
Thank you very much.
All right. Okay.
Thank you.
Right. Yeah.
So goodbye
Okay.
for now.
Goodbye. Yeah.
Yeah. Goodbye.
Shall I stop recording, sir?
Yes, please.
Yes, please. Okay. So now we can leave, right?
Shall I close, sir?
Yeah, I think we can stop. Yeah. Okay. Thank you. Thank you, Jason.